Guys in the room, but right. Okay, we're recording. And Frank, I'm going to turn this session over to you. And we really appreciate you joining us tonight. And if I could hand you a adult beverage over the internet, well, here, try this one. But other than that, please go ahead.
Okay, so let's see. I've got to do the share, so let's see if we can make that work. Let me know when you see my screen.
There you go.
You got it? Good. Okay. Let's see here. There we go. Okay. Okay, so first of all, how many people are in this meeting roughly?
Say again?
Roughly how many people are attending this meeting today?
15.
15. And I wonder how many of you are thinking about some improvements to your receiving antennas? Doug? And who else? Doug and who? Bill, K3WA?
Well, I don't have receiving antennas anymore. All I got is a little 24-foot flagpole.
Yeah.
The good days are gone when I had receiving antennas.
Yeah, I know what you mean. Well, anyway, we're going to go through with the presentation. As Doug AA3S knows, he's been out helping me with my receiving antennas. One of my biggest projects every year is to reinstall my receiving antennas. I have a very friendly neighbor a quarter of a mile away who allows me to use his 4-acre field but only from October through March. So every October I have to install my receiving antennas in that 4-acre field, and every March we have to take them all down. I suppose I could twist his arm and get him to get to use the field all year round, but then I'd have to maintain the field, and I'm not sure that that's any less work. So every March it comes down. But the result is we have some pretty incredible receiving antennas. So there are many choices. If you don't have a great deal of land, there are choices for receiving antennas for relatively small properties. Or if you've got a friendly neighbor, where you can borrow some land for a few months out of the year, there's a lot of opportunities that arise there. That's the route I've taken, and I'm forever grateful to my neighbor for allowing me to do this year after year. Been doing it for 35 years. Thankfully, he's still there, and we still get along very well. So, what's so hard about communicating near or below the lowest usable frequency? And of course, at this part of the sunspot cycle, the lowest usable frequency, sometimes that can feel like 80 meters is there. And 160 meters is really tough. Anybody that operated the CQ Worldwide Phone Contest recently is well aware of how bad 160 meters can be. We operated multi-operator 2 transmitter, which we always do since COVID. And we don't spend a lot of time on 160. Most of the time is on the higher bands, which were incredibly good this past weekend. But you have to spend some time on 160. We work about a half a dozen Europeans, and boy, they were all buried in the noise. Without receiving antennas, I'm not sure we would have worked any of those guys. But the stations in the Caribbean and the northern part of South America were pretty good. Not ideal, but pretty good. And we managed to work, I guess, about 25 or 26 countries, something like that, on 160. In the phone contest, about the best we ever do is about 50, but that's not at Sunspot maximum. So why receiving antennas? Well, they provide much better receiving performance than most transmitting antennas. Their cost is much lower. They do not need to be full size to get excellent receiving performance. You can get very good directivity with receiving antennas with as little as 650 square feet of ground. It's not very much. You can get excellent directivity on a piece of land less than a quarter acre in size. On a larger piece of land, 3/4 of an acre, you can get directivity equivalent to a 5-element 20-meter Yagi on 160 meters. And you can build anybody who's ever tried to build a vertical transmitting array, two-element transmitting array or transmitting four-square, knows that it's really hard because the transmitting elements, the transmitting verticals, interact very strongly with each other from what's called mutual impedance. But with the receiving antennas, you can make the individual elements of the array very lossy. And the result is that the interaction between the elements of a directive array, the interaction is essentially non-existent. So what you usually do in the design of a receiving array is you make the elements lossy on purpose so they don't interact with each other. Now, how can you do that? Well, the reason is simple. Anybody who's ever operated on 160 meters or 80 meters knows that at night you always use your attenuator in your receiver. So why not use that attenuator out at the antenna and get rid of this excess energy and at the same time reduce the interaction between the elements of a phased array? So there's no reason to be worried about losses, especially in receiving antennas on the low bands, because they're your friend. If you don't have losses in your receiving antenna system, you're going to have to use an attenuator to build losses into your receiver. And now some transceivers are becoming available with phase-locked receivers so that you can use diversity reception with two antennas. But diversity reception, unfortunately, requires that the two antennas have to be fairly widely separated in the order of absolute minimum of half wavelength. That's 500 feet on 160 meters, but ideally more like a quarter of a mile or more. And that's pretty tough for most people to get really much diversity advantage on 160. On 80, maybe 500 feet is adequate, and even less than that on the higher bands. There's a measure of the performance of receiving antennas that was developed by W3LPL called receiving directivity factor, RDF. It's a proven measure of the performance of receiving antennas. And EasyNet, which is now a free antenna modeling program, and its output produces its estimated receiving directivity factor for whatever antenna you're modeling. So, but RDF doesn't tell the whole story. Many of us don't live in very isolated situations far away from other houses. It's certainly not the case with me. I've got many houses within a quarter of a mile. And now the primary source of RFI, it seems, is all the different consumer things that pop up in people's homes. It can be as simple as LED lighting, or the little wall wart power supplies that seem to be ubiquitous, and some of those are really bad noise sources, especially some of the ones for laptop computers. And on and on. There's just an endless source of noise that pops up in people's homes. It used to be we worried about power lines, but now it's RFI in people's homes, and then you have to be a diplomat to try to convince a neighbor to cooperate with you, and sometimes that works, and sometimes it doesn't. I've got stories about that I can tell, and for the most part, things have worked out okay, but other times I've had to struggle to find a way to approach someone who didn't really want to cooperate. But in every case, I managed to get the problem solved, and sometimes easily and sometimes not quite so easily. So there's an important difference between small receiving antennas and very large receiving antennas. Small receiving antennas like compact loops that we'll talk about in a bit, they produce their directive pattern very close to the antenna. So small receiving antennas work very well when your RFI source is very, very close, like a next door neighbor's house, and you can't convince that neighbor to help you solve the problem. On the other hand, very large receiving antennas typically have much better RDF, receiving directivity factor, than very small antennas, but their directive pattern doesn't really develop until you're about 1,000 feet away from the antenna in the far field. So very large receiving arrays are not that effective for very close in RFI sources. So you can, and maybe the best situation is to have both kinds of receiving antennas, small ones and big ones. Like some people have heard me say, you can never have too many antennas, and it's true. Okay. So let's talk about small receiving antennas first. Performance of antennas, the RDF of about 7 or 8 dB, it starts to represent antennas with pretty good directivity. So if we look at some of the small antennas that you can consider, probably no doubt the smallest is a small diameter loop. And there's all kinds of those that are made commercially, but honestly, for a couple of dollars, you can make them yourself out of readily available scrap materials, and they perform just as well as the ones that you might buy for $500. They're really, really simple to build. Now, these small loops are produce directivity only for the vertical polarization. For horizontal polarization, they tend to be mostly omnidirectional. And their primary directive performance is a very deep null perpendicular to the small loop. So kind of unlike what you might think about with if you have experience with transmitting quad antennas, for example, quad antennas we're familiar with are directive off the sides, but very small loops have nulls off the sides, and they're very narrow and very deep nulls. And that's what the small diameter loops are really good for, is to eliminate one RFI source. So these loops, the nulls are very narrow in beam width, so they can't null two independent direct RFI sources, but they're really, really good at nulling one. We'll talk about small loops in just a little more detail shortly. Now, the RDF of a small loop is pretty small. It's 4 dB, but that's not, it turns out a small loop is almost omnidirectional, except for those very deep nulls off the side. So it's almost an omnidirectional antenna, so the RDF is small, but the real attribute of a small loop is that very deep null off the sides. It can be as much as 20 dB deep. So often if you have a nearby source, you just orient it towards that RFI source, and then it's kind of omnidirectional everywhere else. If you look at a very simple vertical transmitting antenna or a short receiving vertical, just let's say a 20-foot vertical that you use just for receiving, believe it or not, it has an RDF and it's 5 dB. And you might say, well, how can that be? Well, vertical antennas have a very deep null at very high angles. Directly overhead, the null is extremely deep, but of course we don't get that much interference from directly overhead. So even a simple vertical has 5 dB of RDF, so that's kind of the minimum RDF that's of any value. Some of the hams use beverages on ground. These antennas have very poor low angle sensitivity, especially if they are laying directly on the ground. What you really want to do is to elevate them as much as you can, even if only a few inches. And what some of the owners of these beverage on ground antennas do is they just make sure that the wire is laying on top of the grass and not buried under the grass. And that's kind of the very least you want to do. If the wire winds up buried under the grass, then the performance really goes bad, very bad. The same antenna elevated about 7 feet high has much better low angle response. But of course, it's a little more obtrusive to neighbors. So, and that's the reason a lot of people use beverage on the ground. Unidirectional terminated loops are very popular receiving antennas, and there's a whole variety of these. The K9AY, the flag, the pennant antenna, an antenna called the EWE, and the VE3DO loops are all different ways to use different lengths of wire, all with loops close to the ground, different kind of resistive terminations, and their performance is very similar to one another. There's not much to be said, especially in favor of one or the other. If you have a little bit more land, the VE3DO seems to be very popular. And I'll show a couple of examples of some of these antennas in a couple of minutes. Some of the owners of these small loops will put up more than one in order to get directivity in different directions. Most of these loops are really a little bit too big for you to mechanically rotate them, although some people have done it. And we'll talk about all these antennas in more detail in a moment. If you have room enough to put up short beverages, one way to improve their performance, if you don't have enough end-to-end distance available, is to install a pair of them about 7 feet high. By the way, the reason for 7 feet is just to avoid hazards to humans and animals like deer. So a pair of short beverages works better than a single one, nearly as well as a 500-foot beverage. For receiving, there's no reason to use full-size verticals. It's not necessary. Remember, loss is our friend. So if we don't have loss in our receiving antennas, then we're just going to have to insert loss as an attenuator in our receiver. So we can use loss to help us in the design of these antennas. And 20-foot verticals are all you really need on 160 meters. No reason for tall ones for receiving. And there's a number of popular ways to use more than one. You can use 2 short verticals with very short spacing, 60 to 80 feet. I'll show an example of that. Or you can use a triangle array of 3 of those. They're quite popular. And there's something called the vertical Waller flag, which some hams are using on 160 meters. It produces really good RDF. And it's a reasonably compact antenna. So those were the kind of the low to moderate receiving directivity factor receiving antennas, and these are some of the larger ones. And I'm not going to go through these point by point. Anybody who wants a copy of these slides, just send me an email and I'll forward the slide package to you. If you guys have a web page, we could post these slides there if you'd like. Highlighted in green are some of the more popular higher performance receiving antennas. I would say by far the most popular are beverages about 500 or 600 feet long and 7 feet high, just to avoid hazards to human beings. These are really ideal antennas for 160 and 80 meters. I like them a lot. There's almost nothing you can do to cause beverage antennas not to perform really well. And it's just a piece of wire. It's really, really simple. And I've even had some of these had a tree fall over one, and I never even noticed that it wasn't working. The wire didn't break. And later in the season, I went out and discovered that there was a tree laying on top of it, and the antenna still worked just fine. On the other hand, with more sophisticated antennas like arrays of verticals, every element of that array has to be working exactly correct, or the whole thing doesn't perform at all. It depends on everything working, whereas a beverage is very, very forgiving. One of the antennas I recommend to people with maybe 1/4 of an acre of land is a 4-square array of short verticals. My neighbor W3KX has one of these, 4 20-foot verticals on an 80 by 80 foot plot of land, and the performance on 160 and 80 meters is fantastic. Another popular small array is the YCCC tri-band array of short verticals, and it's only 120 feet long, and I'll show a slide that's focused on that. The Y3CC array also has a 5-element version and a 9-element version. It's basically the same elements, but it just involves more of them and you switch them. And I'll show a slide or two that shows that, a practical example. There's a kind of a controversial antenna, but it performs really well for the few people who've installed them. It's called a horizontal Waller flag, and I'll show a slide on that in a moment. Unfortunately, it needs to be at least 100 feet high, and that's kind of the bare minimum height to get any kind of performance. You really need to be significantly higher than that, and that's kind of a big limitation. So what's the advantage of a horizontal Waller flag antenna? Most RFI produced by power lines, produced by electronic consumers, devices, almost all of them radiate their interfering energy with vertical polarization. Now, how can that be? Why does that make any sense? Well, these RFI sources are connected to some sort of wire that's behaving like an antenna. And in almost every case, these wires are located close to the ground. And horizontal polarization is extremely inefficient when the radiating part of the RFI source is very close to the ground. And most of these sources are very close to the ground. And as a result, the radiation is vertically polarized. The horizontally polarized radiation decays very rapidly with distance. So the reason the horizontal Waller flag works so well is that most RFI is vertically polarized. Unfortunately, you really have to put this antenna really high. So there's only a few examples of this in the entire world. One of them is at N4IS, who is one of the developers of that antenna, and his performance on 160 is just astounding. A PVRC member, W3LPL in West Virginia, has also installed one of these, and he also swears by it. He's worked on people that he couldn't work with his huge beverage arrays. But for most of us, this is just not practical. And then for really big antennas, 8-circle arrays are fairly widely used. The one that I use, 160 meters, is 350 feet in diameter, so that requires about 4 acres. There's a version of that was developed by HiZ, and it requires a 200-foot diameter, and that's also a very excellent choice. The downside to all of these arrays, on the other hand, is that every element of that array has to be fully functional. If anything happens to one of the verticals, or if one of the amplifiers degrades, or any number of other things goes wrong, then the entire array is out of commission and has to be debugged and repaired. That's a whole different story than a beverage where almost nothing can go wrong. And I'll show an example of a really very high performance array. This is wonderful if you've got about 10 acres of land to put it on. And don't forget, when choosing among these antennas, the higher performance antennas tend to be physically large, and they're not very effective at suppressing very nearby RFI because their directivity is not really fully formed in the near field. So small antennas are best for close-in RFI, and big antennas work for RFI that's further away, like maybe 1,000 feet away or more. So let's look at some of these small antennas. Sometimes the small receiving antennas are called magnetic loops. They typically are 8 feet in diameter or less. It turns out these small diameter loops have deep nulls. The smaller the diameter of the loop, the more deep the nulls are. And probably one of the largest of these loop antennas I've ever seen anyone use is 17 feet in diameter. And it still has nulls, but they're about 20 dB deep. And as you go to smaller and smaller antennas, the null depth improves. But as I mentioned, the null is very, very narrow width, typically about 2 degrees. So you have to be able to steer these small diameter loops in the direction of the noise source. Some hams erroneously believe that these antennas are, magic in some way, and you just install them outdoors and they work. Well, that's not true. They work as a result of this very narrow null, and you have to be able to steer that null into the direction of the interfering signal. Otherwise, the performance is terrible. And the other thing that's very important is that the antennas need to be relatively close to the ground. Well, on 160 meters, that's not hard to do because a half wavelength on 160 meters is like 250 feet, and anything less than about 20 or 30 feet high is very close to the ground in terms of a wavelength on 160. But as you go up into the HF bands, like 15, 20 meters, 40 meters, these loops have to be close to the ground because they have no directivity for horizontal polarization. Their directivity is for vertical polarization, and they have to be close to the ground to preserve that directivity. So a much more effective small loop antenna is the unidirectional terminated loop. And there's a whole variety of them. They all work on the same principle. Various articles written about them, and their performance is all about the same. The downside of these antennas is that the beam width of the main lobe is about 120 degrees wide. So if you're trying to discriminate against interference or noise that's anywhere within that 120-degree beam width, well, these small loops aren't going to discriminate against it. Their directivity is their front-to-back ratio. They have quite good front-to-back ratio, but their beam width off the front is really broad. So, there's no free lunch. So that's what these small antennas do, is a really, really good front to back, but beam width is really broad. And these small loop antennas can be mechanically rotated, but not many people do because it's kind of awkward to do it, and they need to be close to the ground to perform well. And it's just kind of inconvenient for most hams to do that. So the history of these antennas goes back a long way. This is the cover of a magazine called The Wireless Age from 1919, and it shows 2 end-fire phased vertical loops. In this little illustration, it shows a building in the upper right-hand corner, and there's a loop on the left side of the building and a loop on the right side of the building, and this is down in the VLF range. And they just use a phasing arrangement to optimize the phasing of these 2 loops. So this is not a new idea at all. This is 115 years old. Just as an aside, there was a huge push during World War I to produce highly directive receiving antennas. This is the very beginning of long-haul radio. And interference was a big problem because electrical distribution systems were not very noise-free, so they had big RFI problems, and not to mention things like thunderstorm noise. So directive receiving antennas were really important, and there was a lot of effort that went into doing that during World War I, and this was one of the more successful receiving antennas, which was nothing more than a pair of phased loops. And this is a diagram of that pair of phase loops. Remember, it operated at low frequencies, well below 160 meters, actually below the broadcast band. And this antenna was 1 mile long. Each loop was 1,000 feet long. And this was just the beginning of the vacuum tube age, so they were able to use not only passive components, but active components in the design of these kind of systems. So this is, again, 115 years old, receiving antennas. And the same concepts apply today. So today we can build arrays of two small loops. It would be unwise to use a pair of very small so-called magnetic loops. These antennas have very poor sensitivity, especially at low angles. So most of the hams who very successfully use arrays of small loops tend to use loops like the VE3DO or the K9AY loops or the flags or the pennants. But then in order to phase them and get any useful performance out of them, they have to be separated by at least a few hundred feet. So you wind up talking about a fair amount of land use. The vertical Waller flag developed the system to be able to place those loops much closer together, but then you have to have very, very low noise figure amplifiers because the efficiency of these antennas is really poor. But their performance is remarkably good, but you really have to pay a lot of attention to details. The horizontal Waller flag in particular, which has to be well over 100 feet high in order to work well, requires more than 40 dB of preamplifier gain with better than 2 dB noise figure in those amplifiers. And it's really hard when people install these antennas to get the system to work well, because any kind of common mode radiation or any kind of other pickup that gets into the antenna or into the feed line or sneaks in through the power line or any other way degrades this system very badly. I mean, you can imagine if you need 40 dB of preamplifier gain, that these antennas are extremely inefficient. And nearby RFI sources require a lot of attention in order to get these extremely inefficient antennas to work well. So let's talk about for some 160 meter operators use these bog arrays with good success. And it's, some people even deploy them kind of covertly in their neighborhood, maybe for a weekend or just a night, and then remove it the next day. It's only 225 feet long, but not laid directly on the surface of the ground. The performance goes really bad when the wire is laying directly on the ground. So just above the ground is what you want to do. For example, just laying on top of tall grass is a good solution. That does require, if it's a kind of permanent thing, you have to go out there occasionally and pull the wire up out of the grass so it's laying on top of it again. Some hams use switchable beverages on ground. That works pretty well, just above the surface of the ground. You can also stagger a pair of these, but now we're starting to talk about consuming much more land. A few hams have installed two wide-space beverages on ground, 350 feet apart, to produce really good 60-degree beam width. But, we're talking about very small antennas, and now with that kind of an antenna, we're consuming 220 feet long by 350 feet wide. So this is about the only attribute of this antenna of such large size is that it's very low visibility. So neighbors might not notice it's there, but if you've got an acre of land, maybe that's not so important. So the wide space bogs are not widely used, but they work really, really well. For people who have some land available, it's hard to beat the performance of a beverage. It's such a simple antenna. There's almost nothing you can do to cause a beverage not to work well. Most of the people who are using beverages use the 500 to 600 foot version, and that's what I have. I have 3 beverages in my system, and that's what they are. They work very, very well. I have one pointed northeast, one pointed south, and one pointed west, and that seems to provide just about everything I need. I've got other receiving antennas too, as you'll see, but the beverages really, really work well, and we get a lot of use out of them. I have tried staggered beverage arrays. That requires a lot more land, And ultimately, we at my station abandoned using that in favor of some other directive receiving antennas. Towards the end of the presentation, I will show a variable phase controller that you can purchase from DX Engineering. It's a very excellent product. And if you want to get the very best performance out of a pair of beverages, this device is really incredible to listen to. But you need to have room enough for two beverage antennas to take advantage of that. And then WHJI down in Georgia has these huge arrays of beverages, a pair of 1,000-foot beverages, 350 feet apart side by side. But the receiving directivity factor is approaching 14 dB, which is something that very, very few people can achieve. So there's a wide range of choices. Some of you have probably heard of the transatlantic tests that were conducted in 1921. Paul Godley, 2ZE, was the ham that was selected by ARRL to go to the UK to perform the US side of this receiving test. By the way, the transatlantic tests were receiving only tests in December 1921, where stations in the United States tried their best to be heard by Godley. He ultimately set up his receiving antenna in a very, very quiet location on the western shore of Scotland, facing right across the water towards North America. And this is a photograph of his antenna as it was installed on the beachfront in Scotland. This antenna was all but forgotten by hams for about 45 years until a very active 160-meter operator, K1PBW, reintroduced the beverage to hams back in the 60s. And they very rapidly became popular and, of course, continue to be popular to this day for people who have several acres available to install them. There's a bit of an oddity to a beverage, and some de-expeditions experience this. They perform best over very lossy ground. Their performance is badly deteriorated over very efficient ground. So if you try to install a beverage antenna on the ocean front of salt water, it won't work well at all because that ocean front has salt water infiltrated into it, and the beverages are omnidirectional. They have no directivity. But if you can place the antenna on lossy soil, like ideal would be a desert, and their performance is the best they can be. And why is that? Well, the reason is very similar to what I talked about earlier about horizontal polarization for RFI. If the ground is very, very efficient, then the losses for horizontally polarized signals are very small, and you start deteriorating the performance of the beverage because it's a very efficient receiving antenna, not only for vertical polarization, but also for horizontal polarization because of the very conductive ground. And you don't want that. So what we want to do is to put beverage antennas over inefficient ground, ideally kind of sandy, dry soil. And then they're very inefficient for horizontal polarization. So that those signals never really make it to the antenna. And that's what we really, really want with beverages, is to put them over very poor soil, not highly conductive soil. So there's kind of two choices for short phased verticals. As I mentioned earlier, for receiving antennas, there's absolutely no reason to use verticals that are any taller than about 20 feet. There's two different alternatives for this. One is called a high impedance vertical, and that's what the high Z verticals are all about. They are typically 20 feet tall for 160 meters, and they have a high impedance amplifier connected directly to the base of each vertical. Very specialized amplifier for a high impedance input. The disadvantage, of course, is you have to have one of these at the base of each one of these verticals. And the method of installation of both the vertical and the connection to the preamp has to be sure that the high impedance is preserved. So you have to use careful installation practices to be sure that that you don't inadvertently reduce the impedance of the antenna and the amplifier by poor installation practices. That's not very hard to do, but it's something you just have to pay attention to. I use these short verticals very extensively in my station. I have 24 of them in 3 different arrays, but I use the low impedance version rather than the high impedance version. So there are some advantages and disadvantages of each. The high impedance verticals can be used on multiple bands. They perform well over, of course, many bands. You can install a high impedance array, the so-called high Z arrays, to cover 160, 80, and 40 meters, and they'll work fine on all 3 of those bands. On the other hand, the low impedance verticals are monoband only antennas. Well, I'm sure you could trick them with different kinds of matching and so on to get them to perform on multiple bands with switchable matching. But most antennas of this type are monoband antennas. One of the advantages of the low impedance verticals is that they are very simple. There's no amplifier out in the snow to have to deal with in the middle of the winter if something goes wrong. They're very, very simple, very low parts count, which leads to very high reliability antennas. It's not hard to build these antennas so that they require very, very little maintenance. Whereas on the other hand, a lot of people with high Z antennas physically remove the amplifiers during lightning season because they're very susceptible to lightning damage. But with the low impedance verticals, you don't have any components like that to be damaged by lightning. Now, one of the disadvantages to the low impedance verticals is you need some sort of a radial system at the base of each vertical. Unlike transmitting antennas, the purpose of the radials is merely to establish a stable feed point impedance. So the feed point impedance does not vary between very wet and very dry conditions. And it turns out that one of the simplest ways to do that on 160 meters is just to lay out 8 70-foot radials, and certainly at my place and many others, that's adequate. And the 4-acre field that my receiving antennas are in, during the course of any evening and night, will probably have 100 or more deer tramping across it during the night. And when I remove those antennas in March every year, those radials are scattered every which way, but it doesn't matter. Their only purpose in life is just to drive the feed point impedance down, and having them in a nice straight line just doesn't seem to matter. So even though they're scattered all over the field, it just doesn't affect the performance. And these radials also provide some decoupling of the coax feed line shield to reduce common mode signals. I'll show you a photograph of the low impedance short verticals that I use. They're 25 feet tall, but there's nothing magic about that number. It can be shorter. And then to make the antenna have broader bandwidth, VSWR bandwidth, I install umbrella wires on top. They kind of look like guy wires, but they're actually conductive wires. So you wind up with an antenna that's 25 feet vertical, and then 4 25-foot wires attached to the top of the antenna that slope down to the ground, just as if they were guy wires. But you can also, if that's inconvenient, instead of using a 25-foot vertical, you can use a somewhat taller vertical and use no umbrella wires, and that works fine also. So there's a trade-off there, like so many different things. So let's go back in a little bit more detail. The very smallest receiving antenna is the so-called magnetic loop. The 8-foot diameter loop is very popular. If a very deep null is very important to you, you can go even smaller than that, but it comes at a price because the efficiency of these small loops gets really bad when they get to be very, very small. So the 8-foot diameter loops are very popular among people that use these. But keep in mind that the benefit of these small antennas is this 2-degree wide, very deep null. And the purpose of this antenna is to suppress a very nearby noise source. And it does so very effectively, but it will only suppress one of these RFI sources. You know, you have to be able to point the side of the antenna directly at the RFI source. Like all very small antennas, these loops produce very low signal levels, requires about a 20 or 30 dB gain, very low noise figure preamp. You can buy these preamps from a number of sources. DX Engineering has them and others. But in order to preserve the directivity of these antennas, it's very important that any signals don't sneak into the antenna system through the power line, through the coax shield. So it's very important to suppress those unwanted noise sources that tend to get onto the outside of the coax cable or into the power cable. And for permanent installations, the people who install these tend to bury the cables about 12 inches deep between the station and the antenna. So they have very little wire exposed to unwanted signals. Now, one of the other aspects of receiving antennas that's very important is that your transmitting antennas, really any antenna, but especially transmitting antennas, and also nearby power lines act as re-radiating antennas. So if you can avoid it, you really don't want to place your receiving antenna very close to power lines. I'm sure many of you noticed that power lines with transformers on them, for example, will typically have a vertical wire that runs down the pole for 35 feet and then to a ground rod. Well, sadly, if you've got RFI on that power line, pretty good chance you do, that 35-foot vertical on the telegraph pole, the electric pole, it's going to radiate noise right into your receiving antenna. So you really want to avoid putting receiving antennas close to power lines unless you have no choice. Especially, you don't want it located near a power pole that has a wire running vertically down the side of the pole. Otherwise, your receiving antenna is going to be coupled right into that vertical wire. So this is a photograph of a 8-foot diameter loop. And, you know, they don't have to be circular. What really matters in the performance of these antennas is the size of the enclosed area inside the antenna. So a quad-shaped or a rectangular shape, just like this one, works just fine. You could make it circular, but it doesn't improve the performance compared to this simple antenna in this photograph. I don't know if this loop is still on that website. I haven't looked at it in a while. It might be, or it might not be. So this antenna works well. It has a 24 dB deep null, about 2 degrees wide. The sensitivity is pretty good. Requires a 20 to 30 dB low noise figure amplifier in order to get any decent performance out of it. But it's not bad for a small antenna. And then the next class of small antennas are the electrically steerable small loops. K9AY loops are popular. The shared apex loop array was very popular, but the company that made it, Array Solutions, is no longer in business. I don't think you can buy this antenna anymore. But all of these small loop antennas have the same Achilles heel, and that is they produce very, very low signal levels. So a good high gain, low noise preamp is essential to get the kind of performance you want. And it's very, very important to pay a lot of attention to choking unwanted common signal noise out of the antenna system. For permanent installations, one of the best ways to do that is to bury the cables so they're not exposed to noise. And you want to keep them away from nearby antennas, towers, and power lines to the maximum extent that you can. I realize that's difficult to achieve in many cases. This is one of the more compact loop arrays that you can build. It requires only a 25 by 25 foot square. It's a pair of K9AY loops. It's really two antennas. They're not phased in any way. So it's two K9AY loops supported from the same 25 foot high fiberglass mast. This produces about 120 degree beam width, so it's pretty broad off the front. Front to back ratio is really good. So a lot of people have room for a simple antenna like that, 25 feet by 25 feet, 25 feet high. The Array Solutions shared Apex loop array was very popular, but no longer manufactured. And I don't know if anyone intends to bring this antenna back in the market. This was a little bit bigger, 50 by 50 feet and 25 feet high. This is the vertical wall or flag array. It's very few of these have ever been built. This example shows a short tower with a rotator, and it's a pair of loop antennas, one loop antenna on the left-hand side and one loop antenna on the right side. If you look in detail at this photograph, you can see that it's two loops, and the two loops are phased. This is a very, very inefficient antenna and requires exceptional attention to detail in order to get directivity out of it. Any common mode signals or signals that sneak in on the power lines will totally destroy the directivity of this antenna. But the performance is really good, but the effort required is pretty large. Not very many of these have ever been built. But then we can go back to 1920, and here's one of my favorite receiving antennas, the Beveridge receiving antenna, patented in June 1921. Still one of the very best receiving antennas you can install. And this simple diagram in the patent is just about all the detail you need to know. A ground at each end, a termination resistor at the far end, and a matching network at near end of the antenna. And the directivity is towards the resistor, as shown in 5 in this patent drawing. And again, I'll say one of my very favorite receiving antennas is the single wire Beveridge. Mine are about 600 feet long. 3 dB beam width is about 70 to 80 degrees, which isn't bad. The RDF is around 10 to 12 dB. This little illustration produced by K9LA in a paper that he wrote shows how the front to back ratio and RDF of a single wire Beveridge vary with length on 160 meters. And you can see why the 550 to 600 foot length Beveridge is very popular, because the front to back ratio peaks with that length. Actually, the very best front to back ratio is the very short Beveridge, but its beam width is very broad, so it's not that desirable an antenna. So this 550 foot one is very popular. Most Beveridge users use approximately that length. It's not that critical. Anything for 500 to 600 feet works great. The other length that's very popular is about 800 feet long, has a little bit narrower beam width, and very good front to back. And then the other length that, because it's so long, not many of them are used, but performance is great, is around 1,000 feet long. Most Beverages are around 500 to 600 feet long. Most of the ones hams use. This is an illustration of a Beveridge on ground. That is, it's really a tripping hazard. You wouldn't want to install this anywhere where people might be walking around. They'd probably wind up doing a faceplant. But this beverage on ground is probably about 12 inches high. And it performs a whole lot better than one that's sitting directly on the ground. This is also a very old patent submitted by Harold Beverage. And this is a bidirectional beverage antenna. And this, as you can see, is not a new invention. This patent was submitted in November 1922. The way you would build an antenna like this today would probably be to use the DX Engineering variable phase controller instead of the electronics shown in here, and then you'd be able to either use it in one direction or the other, or to vary the depth of the null off the back of the antenna. This is an illustration of the radiation pattern of a 600-foot beverage, courtesy of Ari Vors, who did this work. So you can see visually the performance of the beverage. It has some undesired response from directly above, but there's essentially nothing comes off the ionosphere at angles from directly overhead, and the front to back ratio is quite good. The staggered beverage array, again, hams think that we kind of invented this back in the 1990s, but it's not true. This is the patent that was submitted by RCA employee in 1927 that shows a staggered beverage array exactly the way hams build them today, staggered a quarter of a wavelength. So this illustration from the 1927 patent shows two beverages staggered a quarter of a wavelength. You can also do this with bogs very effectively. Most hams, when they build these, stagger the antennas so they're a quarter of a wavelength separation as shown in the drawing, and then the spacing between the antennas is usually about 25 to 50 feet, more or less. It's not critical. And there was an article about this in NCJ back in 2011. And there's the big array that WHJI built about 25 years ago. That was not a new idea either. This is the patent 1927 of the broadside pair of staggered beverages, 14 dB of RDF on 8 acres. If somebody's got an 8-acre field they don't want to use, they don't need to use for anything else. Bad news is 8 acres will give you only one antenna in one direction. So you need a lot of acreage to be able to do this in many directions. So let's look at some of these small vertical arrays. These are very popular antennas. Especially the high impedance verticals are very popular because they're multi-band antennas. The only disadvantage to them being this high impedance input impedance amplifier at the feed point of each vertical. You would have to pay a lot of attention to make sure you do not introduce any stray capacitance in the way the vertical is mounted and in the way the preamp is connected to the vertical. You want to avoid as much stray capacitance as possible in the construction of this antenna. If you buy these from High-Z, they've already done the engineering to keep the stray capacitance as low as it can possibly be. The bad news is that an antenna that's built in this way is extremely susceptible to lightning. So a lot of the hams that have these antennas only leave the preamps out connected to their antenna during the winter and remove the very susceptible preamps from the antennas during lightning season. In order for arrays of these High-Z verticals to perform well, each vertical needs to perform as close as possible to each of the other verticals in the array. So if you have a two vertical array, both verticals need to be installed in nearly identical environments. If you install one kind of right next to a tree and another one out in the open field, their performance will be different and the performance of the array will suffer. Similarly, you don't want to place these close to buildings because there'll be all kinds of electrical wiring and other conductive objects, and that's not good for the performance of these verticals. So you do have to pay attention to where you place them. You don't want to place a high impedance vertical right next to your house or to a barn or a garage, because the conductive objects in the garage will deteriorate the performance of the antenna. Similarly, you don't want to place them very close to other antennas and power lines. This is an illustration of the performance of a simple array of two 20-foot verticals. And it doesn't matter whether these are high Z verticals or low impedance verticals, either one will work equally well. And you can see from this illustration that the real benefit of a two-element array is the front to back ratio. The beam width in the forward direction is very broad, but that null off the back is very deep. This is an illustration of a high Z array that was built by OZ1 RDP. Because it's a high Z antenna system, it has no radials, it has no umbrella wires. It occupies only an 80 by 80 foot square. The individual verticals are only 20 feet high, and they can be made so that they're not very obtrusive. And you get a nice 100-degree 3 dB beam width from this relatively small antenna. It's a very popular antenna. Most hams who build this antenna do so with a high Z components so that they cover 3 bands. And this is the radiation pattern of that 4-square array made out of 4 high Z elements, but the performance is exactly identical with the low impedance elements, but it's strictly a monoband antenna, unlike the high Z. And this is a photograph of a 8-circle array on 3/4 of an acre. So there are 8 of these high Z verticals. Requires no radials, no umbrella wires. This antenna is strictly a monoband antenna, has incredibly high RDF, and the beam width is only 50 degrees, just like a 5-element Yagi on 20 meters. And it requires about 200 feet of diameter, so about 3/4 of an acre of land. And this is what the radiation pattern of the 8-circle array looks like. 200-foot diameter antenna. It's a very, very high performance 160-meter receiving antenna, 13.5 dB RDF, which is just about the maximum you can achieve with any antenna. Another very popular antenna. It used to be manufactured by DX Engineering, but they no longer manufacture it. But there are some ham sources for the printed circuit boards that are needed for the switching for this antenna. If anyone wants to build one of these and you can't locate the source of the printed circuit boards, I can help with that. These can be built in a simple 3-element configuration, which is a switchable forward or back, or you can get more directions with 5 elements or even more directions with 9 elements. But in all 3 cases, there are only 3 active elements at any one time. So in the 2-element array, switchable forward or backwards. The 3-element array is switchable in 90-degree azimuthal steps, and the 9-element array in 45-degree steps. And this is also a multi-band antenna, which is one of the things that many hams find attractive about it. The performance is excellent on the primary band, and still very good on 80 meters and 40 meters, 120-foot diameter. It requires a high impedance amplifier at the feed point of each of the 20-foot verticals. And a lot of attention has to be paid to common mode suppression. So my implementation of these antennas is to use low impedance verticals rather than high Z. So my vertical arrays are strictly monoband, and I'll show the way it's laid out at my place. I use radials. eight 70-foot radials on each vertical, just randomly scattered on the field. It doesn't matter. If you go through a lot of effort to lay them out straight, in a few nights the deer will reorganize them, but it doesn't matter. My verticals are 25 feet high with umbrella wires at the top of each vertical. That looks just like guy wire. You can use taller verticals if you don't want to use the umbrella wires. These can be built with as little as 65-foot element spacing. It's best with these short spacings to use a variable phase controller, and I'll show you the DX Engineering one in just a moment. You do not need amplifiers at the base of each vertical, so it makes the system much more reliable. You don't have to worry about electronics buried in the snow. And these antennas are very easy to build yourself. You may recall for the high impedance vertical, I pointed out that it's very, very important to avoid as much stray capacitance as possible with the high Z array. Well, with these low impedance arrays, they're extremely tolerant of varying construction practices. So that's a very nice thing about these low impedance verticals. The downside being they need radials, and for most of these antennas, you need top hat wires, but they're very easy to build out of scrap materials, really. You still have to be careful about where you place them. You don't want to place it very close to power lines or nearby towers. And you can get about 12 dB of RDF on a quarter of an acre with 4 of these antennas spaced about 80 feet apart. But they're strictly monoband. This is a photograph of one of the verticals that I use in my arrays. I have 24 of these verticals in my receiving antennas. And if you look very closely, you can see the 25-foot vertical. And then a little bit harder to see are the 4 umbrella wires. And this field is populated by many, many deer at night. So it's important not to run the support rope all the way down to the ground, or the deer will trip over the support rope. So the rope that attaches to the end of the umbrella wire connects to the top of a 7-foot fence post. And I've never had a problem with deer getting tangled up in these antennas. Not to say it isn't going to happen, but it could. And the foundation for these verticals, any of these verticals, is very simple. I'm a temporary user of this 4-acre field. I have to remove all these antennas in March each year. So what I use for a foundation is very simple. It's a 2-foot length of 1-inch diameter rebar. And the vertical just plops right down on that piece of rebar. And then at the end of the contest season, just go out there with a sledgehammer and pound on that rebar a few times, and it pulls right out of the ground. So it's an excellent temporary foundation for an antenna like this. Takes only a minute to install it and about a minute to remove it. Couldn't get easier. And rebar is very inexpensive. And this is the pattern of the big 350-foot diameter 8-circle array that I use on 160, 80, and 40 meters. And this is the layout of my receiving antennas. The black dots show the 25-foot tall low impedance verticals on a 350-foot diameter circle. The red dots show the 80-meter verticals. They're located inside the footprint of the 160-meter verticals. So they're on a 175-foot diameter circle. And then my beverage antennas, the 3 of them run right through the middle of the array. And there's no apparent degradation of either the verticals or the beverage by running them this way. And why would that be? Because there's almost no mutual impedance between these antennas. They're very lossy the way they're built. But remember, on the low bands, loss is your friend. So you can use the lossy nature of these antennas to engineer antennas that have almost no interaction with each other. If you tried to build this array out of very highly efficient components, you would have a great deal of interaction between these antennas, and the performance would be really, really hard to optimize. So you actually use loss to your advantage in engineering a system like this. This is the variable phase controller that I mentioned. The current version of this is called the NCC2, manufactured by DX Engineering. It's an excellent way to combine inputs from two antennas, such as two staggered beverages or two 25-foot verticals. It's very, very easy to use and very, very well engineered. And I have many of these K3 transceivers in my station. One of the great advantages of these, if you have two receivers, they're phase locked. So they work really well to put one receiving antenna in one receiver and another antenna in the other receiver. What we usually use is to put the transmitting four square in one receiver and a quarter of a mile away, one of the receiving antennas in the other receiver. So that's the end of my story. If anyone has any questions, I'll be happy to address them. You can also send me email at any time. I've had the same email address for many years. And you can drop me a line and I'll be happy to try to address any questions you might have that way. So back over to net control.
Thank you, Frank. That was a great talk. And it makes me think back to the days when I had a shared apex loop. I had 550-foot beverages, and then I had a 1,000-foot north-facing one to get those real weak ones over the pole into Asia. And now I have a flagpole.
So did you install those beverages in 1921?
Pretty close. You subtract a few years, I feel better, but most days I feel about that old. But anyhow,
It's
for
amazing
everybody else,
it's amazing how hams kind of forgot about beverage antennas for almost 50 years.
yeah, that's a fact. But for everybody else who has a real question, and oh, by the way, if anybody needs one of those small loops, which does not work when it's right up against the side of my house, it's free to a good home. Anybody have any questions for Frank? If you speak up.
Yeah. Just a question about operating.
And who is this?
Yeah, the question about operating.
Tell them who you are.
Oh, hey, Frank Wayne, KU4V.
Hi, Wayne.
Yeah, just a question about operating. We at VP5M, we heard W3LPL on quite a bit. I think we got you in the log. We did not hear you that often. So could you comment how you use these receiving and when you get on? Is it the top of the hour, starting at 10 or 11, or if that type of question makes sense?
Yeah, that question makes a lot of sense. So back before the pandemic, we used to operate multi-operator, multi-transmitter. One of my operators died during the early days of the pandemic before anybody knew how to treat it. And that caused some consternation among some of the other operators, and some of them decided to drop out of operating with us after that death occurred. So we scaled down during the pandemic. You remember those bad couple of years, to multi-single operation with very small teams, and I re-engineered the layout of the room to have better air circulation and more isolation between the operating positions. Well, the team has shrunken now. We used to have about 14 people, and the pandemic caused the size of our team to drop down to about 8 people. So since the pandemic, we've been operating mostly multi-2. And of course, now we're right at solar maximum right now. 15 meters is open all night long. 10 meters is open from sunrise until at least a couple of hours after sunrise. And the conditions are just incredible. We worked almost 3,000 QSOs on 10 meters last weekend. Actually, the weekend before sweepstakes, 10 days ago. So we didn't spend that much time on the low bands. And these kind of receiving antennas, their big advantage is on 160 and 80 meters, and probably in the entire 48 hours, we were probably only on those two bands for a couple of hours each night. We were distracted by solar maximum, operating on the higher bands almost all the time. But we don't follow any rules like operating on the hour or anything like that. Of course, in a multi-operator system like we have the spotting network, so they kind of tell us what's going on the bands all the time. So we're very reliant on the reverse beacon network on CW in order to tell us what bands are open where and what might be there. So we're dependent on the network and on the logging software to help direct what bands we're on rather than any preconceived idea about, kind of being on the air at the top of the hour or anything like that. So I'm sorry that was a little bit of a complicated answer for a simple question, but bottom line is we use the reverse beacon network and computers to drive our operation these days. Any other questions?
Anybody else?
K2TNO, Bill?
Hi, Bill.
Yeah, hi, Frank. Really interesting as usual. A quick question, and that has to do with susceptibility of your receiving system to lightning and to induced EMF just from passing storms, and how close they get before you begin to get worried that something's going to get fried in the shack. Could you comment on lightning as opposed to atmospherics and other types of QRN?
Yeah, well, of course, that's one of the reasons that we don't use the high Z antenna. So we use the passive, both the beverages and the verticals are all passive. There's no electronics in the field at all. All the electronics are in the ham shack. And our approach to lightning protection is very brute force. If there's a lightning storm anywhere in the vicinity, which means less than 50 miles, we just disconnect everything because we're on a fairly high ground. There's nothing higher than us for miles around, and we're very, very susceptible to lightning. So if there's a lightning storm nearby, we don't take chances with the operators or the station equipment. We just disconnect while that lightning's in the area. We're off the air, and when the lightning storm is gone, then we'll connect things back up again. We don't take chances. Of course, there are other approaches for lightning mitigation, but that's the approach that we use.
Thanks.
Any other questions? Well, I want to thank anyone who may have voted for the article that I wrote that appeared in October QST. I just got a telephone call from the Atlantic Division Director yesterday that said that that article won the best in the issue, October QST article. So thanks for anybody who voted for that article.
All right, that's great.
Okay, anyone else with a question for Frank?
Hey Frank, can you hear me?
Yeah.
This is Steve, W1ES. I've got a lot of trees out behind my house. Do any of these work close to trees?
The low impedance verticals are a better choice
Okay.
than the high Z verticals. When you're close to trees, the trees don't matter. For the low impedance verticals, it doesn't matter. But for the high impedance verticals, it makes a big difference. And the other thing is, if you got room for beverages, they don't care either. You can run a beverage right through a forest, it'll work fine.
Yeah, I've got about 3/4 of an acre and it's all wooded. So
Yeah.
it's not easy.
Yeah, well, if you can find a way to put a low impedance vertical in there, it'll work just fine. It won't be affected.
Thanks, Frank.
Okay, let me interrupt just for a second. The way staff is going to be coming in with our checks real soon. And thank you for taking such good care of us tonight
And your patience.
and her patience. So before you all leave, when you get your check, please do take good care of her, okay? Get those tips up. All right, back to everyone else with questions for Frank. Anything? Frank, I guess that's it for tonight. Thank you so much for joining us. It was a great presentation. And as soon as I can figure out how to fit this on a postage stamp lot, I'll be building.
Fine. So if anyone wants a copy of these slides, just drop me an email and I'll forward the slide package to you. Or if anyone has any questions, you can just drop me a line at my email address, which has been the same for the last 30 years.
Yeah, I would love a copy. If you could, Frank, I can send you an email if you
Yeah,
want.
just send me an email and I'll respond to it right away. So good night, everybody. Have a
Good
great
night.
time.
Thank you.
Thank you.
73.
Thanks a lot, Frank.
Okay. So, as Frank